share my screen.
Mm-hmm.
Let me know if you can see it. It should be just like the name, the whole name of my presentation. Can you see it, Mayra?
Yes.
Yes. Okay.
Yes.
Perfect. There you go. Okay, so good afternoon, everyone. I'm Dr. Alejandra Castellanos. So today I'm going to talk to you about a little bit about what I do, my research, which is on the computational framework for durability of laminated composites and sandwich composites at extreme environments. So first, I'm going to start first with where I'm coming from. So I'm a graduate from the University of Wisconsin-Madison. So the picture that you see on the top, that's actually one of where the university is in Wisconsin. So recently, UW-Madison was UW-Madison was recorded as the 32nd best school in the world. So I went to study there through a fellowship, which is the GERS Fellowship, which is the Graduate Engineering Research Scholars. And there's a picture of me on the day of my graduation. And then on 2017, I was awarded the Amelia Earhart Fellowship, which is only awarded to 35 women every year globally, who has done significant contribution to the aerospace industry. In this case, I was doing some interlaminar reinforcement for composite, which I will talk a little bit more about that project. So I was awarded that in 2017. But I'm also a UTEP grad student. I'm also a UTEP alumni student. I got my bachelor's and my master's from UTEP in the mechanical engineering department. So the picture that you see on the top, that's actually like on the 2014, the 100 years of the university, that graduation, which was in the Sumble. And then you see one of the pictures with Dr. Cesar. He was my senior advisor. And then another picture with some of my friends when I was a master's student there. So after I got my master's at UTEP, I went to UW-Madison for my PhD. So where I have been doing research, well, I have been on the Institute for Advanced Composite Manufacturing Innovation, Purdue University, Volkswagen, the Air Force Research Laboratory, Boeing, ONR, and on the picture that you see at the bottom, your bottom right, there is a picture of me on one of the internships on IACME. And the picture that you see on the left, this picture, I think, yeah, this one is the Center of Composite at Purdue University. So it's one of the biggest composite center there is in the United States. All that whole building is just composite materials. So based on that, as you can see, I work on structural composites. I look into their manufacturing, materials, and mechanics to know what type of failure mechanisms composite will have. Then I found what is the damage, some damage mitigation techniques. So I try to prevent those failure mechanisms. And then I study their whole life at extreme environments. So my work is a combination not only of just experimental work, but also I do a lot of computational work. And something, some students have asked me, like, if I use a composite for only carbon fiber or glass fiber. Any structure that you have two materials with different properties, that's a composite. So I study all that. My focus, most of my research is on polymer matrix composite, which I will talk about the projects that I have. But I also work on other types of composites, like carbon-carbon composites, or also for coatings, for thermobaric coatings for engines. So just so it's clear, I'm not only do just composite, just polymer matrix composite, but we look through all, whenever you have two materials that you're putting together, that's what my group is studying. And again, for this, we do everything in my lab, from the manufacturing, the testing, and the computational work, and the post-processing of all the data. We do that because that way we know the conditions that the material was manufactured. Because if we buy material from another company or from other places, we don't know exactly the manufacturing process that they are using. And composite is very sensitive about the manufacturing process. And they don't provide all that information because, again, that's research that they are doing too. So they don't provide all this information. That's why everything we do, we manufacture ourselves, test it, and do the computational model. So what are polymer matrix composite, which is one of the projects that I work the most? So polymer matrix composites, they are used either on marine industry, definitely aircraft, aerospace, and pressure vessels. There are also other recreationals, such as for recreation, such as golf. The one that I have seen is golf, bicycles. So there's like a lot of different applications of polymer matrix composites. So the picture that you see at your top left, this one is for pressure vessels. And then here there is a ships. So we look also to see how to replace the ship hull with a ship hull made of composite. And then the picture that you see at the bottom over here, this one is just honeycomb. And then also like airplanes and aircrafts that we use. So what is a polymer matrix composite? Well, a polymer matrix composite basically are fibers that are reinforced in a polymer matrix. All these layers are stacked up or layered up to create a laminate. So one of the most important things, well, one of the still challenges that we have in composite materials is that the mechanical properties in the implant mechanical properties, which mean where we have the fibers, which will be Y and will be the X direction. Those mechanical properties are really good, are really strong, very steep. The problem or the challenge that we have right now is what's going on with the interlaminar region. The interlaminar region is a resin-rich region between each of the layers of the fibers of composites. So this, because this part is very susceptible to damage, that part of that resin-rich region it's always a big problem. And when we have this different failure mechanisms in composite, usually start with the lamination, which is the separation of the layers due to that interlaminar region, which is just resin-rich region. But why do we still use in composite if we have the problem? Well, because they have really high specific strength, high specific stiffness, lightweight, low thermal conductivity, and it has tailorable mechanical properties. It has really, really good properties, so that's why we still use it. So one of the projects that I'm going to talk about today is about the impact damage tolerance enhancement. So as I was explaining before, this resin-rich region between each of the layers of your composite is very susceptible to damage. And just so you have an idea of why we have this, usually the layers of the fibers have a Young's modulus of 125 gigapascal, but this resin-rich region, the Young's modulus is 3.5. So it's really small. So that's why we have this different coefficient of this different, the difference between the Young's modulus will make this that all the damage is going to start on the resin-rich region. So one of the cases of loadings that we use and that we investigate and still is a challenge is the impact on laminated composites. So the picture that you see over here in your left, the top left corner, that's a laminated composite, and the picture that you see on your top right, that's a sandwich composite. So if you see, for a sandwich composite, we have two face sheets that are made of carbon fiber, and then between those, we have a polymer foam. So that's also one of the structures that we investigate in my lab. So what happens when you impact a composite? For example, it could be because there is a drop tool or debris, or for example, like a bird that hits the airplanes. All of those, we divide the impacts in low velocity and high velocity. So high velocity impact is this one, which is your lower right corner, as you can see here. So in high velocity, it's pretty easy to know that we have a damage because you can see the perforation exactly of the bullet or the striker or any other damage that it could happen. However, the problem that we have in composite, or the challenge that we have, is the low velocity impact. Because on the surface, as you could see on this picture over here, the surface doesn't have any damage, but that doesn't mean that inside your composite, you're not going to have the damage. And on this ones are micro CT pictures, as you could see over here, that shows actually the damage that is inside your composite. So the problem with the low velocity is that it will produce damage that you don't know is there. And what happened is that the structure can just fail catastrophically. Because if you see in a high velocity impact, you will see, okay, there is a damage. So we either have to replace it or we need to repair it. But in the low velocity impact, you don't know exactly what is going on inside. So that's one of the things that my research group studied. And when in the case of the low velocity, there will be a reduction of stiffness and strength after this foreign objects impact the laminate composite. So obviously, this is not something new. There has been a lot of through-thickness reinforcement that people have been studying in the past, like C-pinning, where they use pins or needles that they use an ultrasonic gun to push the C-pins on the through thickness of the reinforcement. Also, there is a stitching where you use a needle and a thread to completely perforate each of the layers of the composite. We also have 3D weaving, carbon nanotubes, zinc oxide nanowire, and shop Kevlar. So there have been a bunch of studies with this, so to prevent that separation, to reinforce that interlaminar region. But again, still one of the problems with all of these methods is that they reduce the in-plane mechanical properties of your composite. So why is that? Because in the case of the pin, even though, yes, they increase the through thickness reinforcement, they will prevent the laminate to separate the two layers of fibers. There's still one problem, and that's that this pin will break your fibers as you are perforating it, as you are perforating your composite. So that will damage your in-plane properties. With the needle, is the same. When you start using the needle and the thread, all those fibers will start breaking. And then another problem on your top right hand over here, as you can see here on this picture, is that on the pins, when you put it, you will see some resting pockets around the pin. So that's a big problem because that's where the lamination or damage will start. Remember that always cracks will try to look at the path of less resistant, and the less resistant on the composite will be on these resting pockets. And then in the case of the Kevlar chop, there has been an extensive fractures and fiber pullout, as you can see here. And obviously there is carbon nanotubes, but the problem with the carbon nanotubes is that when they start applying the carbon nanotubes on the layers of the composite, they do not distribute uniformly. They tend to agglomerate. So you will have a part that is really, really, really reinforced, and then the other part of your composite, there will be no reinforcement at all. And in the case of the zinc oxide nanowires, it takes a long time to process all of them, like around 8 hours. And also it takes the way that it is meant, the way that we grow the zinc oxide nanowires on the fibers, we use some beakers, and the beakers size is obviously one of the biggest limitations to make this process kind of like in larger scale. So those are the problems that we have. So we have figured out a way to increase the strength of the interlaminar region of the resin. But again, this is still in the process of development. So I'm just going to tell you that we figured out a way to do this. So as I told you, in my lab, we do everything from zero. So we manufacture a composite. So this big machine blue that you see there is a compression press. It's a compression press machine in which we manufacture a composite. After our composites are being manufactured, we use a water jet cutter. So we also have that in our lab. And then we produce, as you can see in this picture, the laminates exactly to the dimensions that we need for the testing. So with this new method that we're using, there is no reduction on the in-plane mechanical properties of the composite. And also we're increasing the impact damage tolerance in our composite. Again, this project is something that is going on, so I cannot disclose all this information with you, but we have figured out a way to increase the damage tolerance. And it was around 20% of the damage tolerance increase. So where do we do all this testing? So the machine that you see here at the bottom is called a CA9340 drop weight impact machine, which consists of a striker that would hit exactly the center of your composite. And then the door, that white door that you see over here, that's an environmental chamber. So in my research group, we don't only see what happened at room temperature, because you will never have any you will not only have that your composite will be always exposed to just room temperature. You have different environmental conditions such as low temperature, like for example, if you have a ship that is going through the Arctic, your ship might experience temperature up to minus 60 Celsius, which are the temperature that are in the Arctic. But also they can experience really high temperature. In the case of the ships, this high temperature could be between 60 to 80 Celsius. So obviously we need to know not only what is going on at room temperature, but also what is happening at these different temperatures. So for this reason, we have this environmental chamber. So the test that we do in my lab is room temperature. We do also very low temperatures, minus 60 Celsius, and also really high temperatures for 80 Celsius. Now, 80 Celsius, that's only for the ship's hulls. Obviously, we test other composite at higher temperatures. So again, all of this, we have found out that there's a reduction of around 20% in the damage by adding this new interlaminar reinforcement. So we're currently in the process of developing an impact model because, as I mentioned before, my research group not only focus on manufacturing laminates and see how the materials fail and why they are failing, but also we look at how we can create computational tools that can predict that damage, that can tell you, okay, if you impact to with a certain mass or with a certain velocity or with a certain impact energy, what will happen? Obviously, all these tests for composite are very expensive to do. So that's why we need very reliable computational tools that can predict the life of our composite. And this project is currently done by my PhD student, Zach Nieto. So he's currently working now on the computational part of this project. And again, we've got really good results with a damage reduction of around 20%. Another project that we have is composites in extreme environments. So as you have heard probably, NASA announced that they want to go back to the moon by 2024. But one of the biggest challenges that we have is with the cryogenic propellant tanks, because they will be exposed to cryogenic temperatures, to extreme thermal gradients, and gravitational loads. And in the moon, the environmental conditions, you're going to have lunar dust, extreme temperatures, which range from minus 233 Celsius to up to 197 Celsius, radiation effects, thermal effects, vacuum effects, and thermal gradients too. So to assist with to make sure that we get to the moon in 2024, carbon fiber reinforced polymer composite have become a solution to use as a cryogenic propellant tanks. And again, that's because they have lightweight, low thermal conductivity, high resistance to fatigue, and they have really good tolerable mechanical properties. So obviously there has been other studies in the past where they have tried to see how they can use these tanks at cryogenic temperatures. And for cryogenic temperatures, we are talking about temperatures that are minus 200 Celsius. So that's why it's really extreme. So there has been a lot of trials to do for the cryogenic tanks. One of those was the DCXA, which was made of prepreg. Prepreg are layers of composites that are impregnated with resin. And in the DCXA, they use unidirectional prepreg. Unidirectional means that all the layers of fibers are pointing in one direction. So that was the first composite cryo tank that they did. But after a while, they just stopped with the project. And then they start with the project with the X33. And again, one of the big problems that they found out is the lamination. And remember that the lamination occurred because of the interlaminar region that is very susceptible to damage. So we're still having these problems. And also they found that there was a lot of propagation through the unidirectional prepreg. So learning from the X33, the Space Launch Initiative Composite Cryogenic Program, they decided to use a sandwich structure. And if you remember, the sandwich structure is made of two phase sheets that are bonded to a thick core. And what they did is that they didn't use any, that in this case, they used an aluminum liner to prevent any leak on the tank. But again, these two projects, they just canceled the projects. They didn't mention why. It wasn't because of composites, but they just canceled the project, but they never disclosed why they did that. But then they had the CCTD, or the Composite Cryogenic Technology Demonstration Project. They actually were able to manufacture one of those cryogenic propellant tank made of composite. But instead of using unidirectional, which all the layers are pointing in one direction, they use plain weave or woven fabric. So this will prevent the propagation of with the woven. This will prevent the leak or the cracks to propagate faster than in a unidirectional composite. So following this, we decided to start also working on finding out on developing a high fidelity computational models that will be able to predict how the composite will behave at this extreme temperature. But again, there is another problem or another challenge that we have faced, and that's that all the environmental chambers, as you can see here on your left, those are environmental chambers that are attached to the machine. And again, those are to test at different temperatures or room temperature. So what the problem with these environmental chambers is that those chambers expose all the sides of your composites to a specific or to a given temperature, which is not the case, is not a real scenario, because in composite or in any other structure, you will have that only one face of the composite is exposed to a certain environmental condition, which could be seawater on ship's hold, extreme temperatures like on this pressure vessel. So we need to find a way to know that if we only expose one part of the composite to a certain temperature and then the other part to the other environmental temperature, how will the mechanical properties of the composite will be predicted? Because so far, most of the studies that have been done until this date, all of them, they just expose the whole composite to the whole to the environmental condition in all the sizes, in all the sites, which is not true, because one of the phase will always be to one environmental condition and the other phase will be exposed to another environmental condition. So what we are doing, as you can see here on the top, those are some samples that my students manufacture. And again, this is the laminate where we took those samples. And for this laminate, we use our water jet cutter. So we figured out a way to just expose one side of the composite to a given temperature and the other side of the composite to another temperature to mimic what a real scenario will look like. Because again, remember that what we have been doing, or what it has been done in the past, is just expose the whole composite to one environmental condition, which we have found out, and a lot of researchers have been reported that because this is not a realistic scenario, the failure mechanisms, what is going on inside your composite will change when you have this thermal gradient effect. So we figured out a technique or a way to keep this composite while we're testing to two different temperatures. And again, I cannot disclose this because this is a project that is still going on, but we're working on publishing this work. So how this relates to the pressure vessels that we have? Well, from all these different tests that we will be doing, we're going to use these properties to use as an input for our modeling. So these are some modelings for a pressurized vessel, a composite pressure vessel, as you see over here. So this project was started by my students Lucero Buendia and Itzel Torres. And Lucero is in the Aerospace Corporation right now, and Itzel, she's still deciding if she will go to the Navar or to Lockheed Martin. And this project is continued by my undergrad research assistant, Sarah Abed, who is also a Curdy awardee for this fiscal year. So another project that I'm working on is on the non-destructive evaluation of composites. So as I mentioned to you, damage in composite is really, really hard to detect when there is not a very big damage that we could see, like a perforation, because always you will have this fiber fracture, for example, in letter A, which is the fiber fracture, letter C, in which the fibers are pulling out of the matrix, as you could see there, and then letter D. This one is just the striker completely perforated that composite. And letter E, we have the lamination, which is the separation of the layers of fibers because the resin-rich region is very weak. So why are these a problem? Because when a composite failure fails, it just failed catastrophically. It won't tell you like, okay, I'm just, it's going to start leaking and then it's going to fail. No, when it fails, as you can see here in these pictures. And then on these pictures, on the ones that say 25 Celsius, 0 degrees, and minus 25 Celsius, those are micro CT scans of the sandwich composite at 3 different temperatures. So this sandwich composite was impacted with the striker, and then we evaluate how the temperature affect the sandwich composite. And as you can see here, as the temperatures are decreasing, the penetration of the striker through the foam starts to increase, which means that at lower temperature, the material will become more brittle. So there are obviously current non-destructive evaluation techniques, such as infrared cameras, for example, ultrasound, or also, the picture that you have on your top left, that's ultrasound. And the picture that you have at the bottom is for a thermal camera. The picture that you have on your right, on the right bottom corner, that's with a micro CT scan. And the picture that you have on the top, that's also with the thermal camera. So there are currently a lot of non-destructive evaluation techniques, but again, all of them have some issues or have some challenges. For example, in the case of the ultrasounds, sometimes we need to add like a liquid that will help us to determine what type of damage is inside. And all of this evaluation technique doesn't tell you the damage that is happening at that specific moment. Instead, it tells you after the failure has occurred. So we need to find a way to detect when damage is occurring at that exact moment. And for that, we need to add some sensors that we can capture when that damage is occurring. So for that, I'm working on an optical fiber project with Dr. Quintana. We're doing some collaborations in which we're using optical fiber that will be embedded in the composite, which will act as the sensor located at critical locations. And for this one, we're trying to do in 2 different ways. One, that we're trying to cure the laminate with the optical fiber inside. And the other one is when we are attaching the optical fiber after it has been cured. So we're trying to do that. And why? Because we want to be able to know what is going on inside our composite. We want to have in service structural health monitoring, strain measurements, loads monitoring, damage detection and quantification, and obviously we want to know the impact monitoring. But this project cannot just be done by just one person. It has to be an interdisciplinary research. So Dr. Quintana, he's an electrical engineer, so he's helping me with the electrical part of all these sensors. And in my group, I have also a career awardee, an undergrad research assistant, which is Alan Terrazas. So we are assisting with the part on the solid mechanic part, which are all the stresses, all the strains. So this is an interdisciplinary project that we're doing with him. And my last project that I have is on hypersonic and thermal barrier coatings. So for hypersonic, this is a project that I have with Dr. Stewart and Dr. Rahman. So we're trying to see about in hypersonic, the temperature that this vehicle will experience are higher than 1500 Celsius. So obviously at that extreme temperature is really, really hard. Do we have a lot of failure mechanisms? So we want to understand what type of coating we need to use in these hypersonic vehicles so that they will last, so that they will be able to perform whichever duty they have to do. So for that, we're looking into a coating for hypersonic vehicles. We're looking into a coating that will have ablation protection, EVC crack healing, oxidation protection, and bonding. And if you see in this picture, at the end we have carbon-carbon composite because there is no way we can just use one material in hypersonic that we can use for the whole thing. We need to use coatings so we can prevent this. So we can prevent failure between the material that will be used for composites. So from here, if you see, we are using different materials to create. We're using different materials to create this coating. So now, so far, everybody knows how just carbon-carbon composite works, or how silicon carbide works, or how the silicates and additives work. However, there hasn't been, until this date, there hasn't been a whole understanding of the whole coating. So we need to know what exactly is happening as the whole structure. And for that, obviously, again, for this, we need an interdisciplinary study in which Dr. Stewart and Dr. Rahman were trying to see what is exactly that coating that we need. And then the other project that I have is on thermal barrier coatings. So, as you know, on the engines, they will be subjected to really high temperatures when they are working, like around 1500 Celsius. So obviously, there will be some debris that will go inside your turbine, and then this debris will start melting on the fans, as you see over here on letter E. You will see that that debris will start damaging those your turbine. So what people have seen is that the main failure mechanisms that we can see on the thermal barrier coatings is the lamination, cavitation, the lamination on the bond coat, and some vertical separation. So even though I work in composite, this type of failure mechanisms, we also see it in composites. Instead of cavitation, as they call it here, we call it voids. Instead of and again, we have the lamination, as I have explained to you, which is the separation of two layers. So the same failure mechanisms that the thermal barrier coatings are suffering are exactly the same failure mechanisms that we can see on composites. So that's what we're trying to work is up using the loss from composite, apply them to the thermal barrier coatings and see how all of this how they are affecting these coatings that we add over here. And why is this a big problem? Because again, a coating is different materials that are put in together to give some reinforcement, either as a thermal barrier. But the problem with this is that because you're using different materials, you have this difference in the Young's modulus. So because of that, there is a coefficient of thermal expansion that will be different for each of the materials. So that's why this type of mechanism will start to happening, like the lamination, attacks, cavitation, all these different failure mechanisms will start to be present. So we need to know when will it start, and we need to know how it will progress. So once this failure mechanism starts, how it will progress. Will it damage completely the turbine, or can we use it for 100 more hours service? So all of those things, we need to know how it will behave. And again, to be able to produce this type of analysis, just experimental, first of all, it will take a lot of time, and also it will be very expensive. So for this, we're developing computational tools to see how this damage will propagate, and once it starts propagating, how long do we have, or how the life of the turbine will be reduced. So this thermal barrier coating project, which is mainly simulations. This one is done by my master's student, Edgar Avalos, who just joined my group project, my research group this fall. So that's it for the projects that I work. And again, I cannot give you too much details because those are all the projects that are going on. I just want to give you a brief introduction of what I'm doing. So some of the students, because I remember when I was a student, I didn't even know how to get started with research or how to start working in something. So my advice from my experience is that you have to ask these students who are already working with one of the professors, check the professor's webpage. Most of the professors have a webpage. So make sure you go and check what projects do they have. And also look for on-campus opportunity like CURDI if you are, in the case you're an undergrad. If you are a grad student, apply at the CSETR. So make sure that you identify which professor you well, not which professor you like, but like identify what are the classes that you enjoy the most, and or are very interested for you. That's the main point, because research is something that it will take you. Even if you know how to do research, there was always 100 things that will probably go wrong, and you need to have a lot of patience when you're doing that. And if you're doing that for something that you don't like, it's gonna be a nightmare. So no, make sure that you do something that you like. And obviously ask your professors. But my advice is first, go and check their webpage or talk with his graduate students or undergrad students and ask them, hey, how do you start on research? What is this professor doing? Do you like your project? Do you like working with them? That's the best way to start knowing with whom do you want to work. And definitely volunteer to learn. Now, this doesn't mean that you're going to get to the lab. Obviously, this is setter, which because we all work for the setter, you need to be appointed to go to the lab. But if you volunteer with a professor to start reading some papers or to start working with simulation, that will be the best way that a professor will know that you really want to be part of their group. For example, my two undergrad students who got the Curdy Award for this year, they talked to me last fall. So I told them, you know what, there is Curdy, this Curdy Award that is open